We had some technical difficulties. So as I was saying, you have to calculate the area of each shape. Hit it. So let's just say, hypothetically, this is 3 inches, this is 3 inches, this is 6 inches, and then this will be 3 inches and 3 inches, right? So this times together is 18, correct? This times together is 9, 3 times 3, and then finally 5. 1.5, 3 times 3 divided by 2. Then you have to find the centroid of each one, like I said before, right? Remember? So this would be 3 divided by 2, 6 divided by 2. So your centroid can be found at 3, 1.5. 3, 1.5. This would be found at 1.5. And then this, since it's a triangle, remember, you gotta find this, which is the height. This side, and then this side, divided by 3. Since this is 3, divided by 3 is 1, so 1. And then since this is 3 divided by 3 is 1. So this is where you find all of your centroids. The next step is you have to multiply each simple shape's area by its distance from the centroid to the reference axis. Now the reference axis is the one solid line. And this is that this, it sounds like a lot, it's really not. It's this area right here, this line. So it's distance from the actual axis for x and then y. So you want to make a table kind of like this. So the distance from here to here is 1.5. And then this is on the x. So this is only an example. I'm not going to walk through the entire thing. Okay. 6 times 1.5, right? So the entire area is 18. And then since the distance from here to here is 1.5, it's 18 times 1.5, which equals 27 inches. 27 inches. This is the first step. So to speed up the time, I simply wrote out every single one. So this is 18.3, which is this, and 18 up. 18 times 3 is 54. 4.5, which is the area of this one, times 4, because it is positive. I had messed up which shape was which. This is the 4.5, right? And since it's 4 away from the axis, that equals 18, right? 18 for the x. In this direction, it's 4 away. And then up, it's 3 plus 1, so 4. So it's also 4. So this is 4.5 times 4, which is 18. Finally, it's 9 times 1.5 upwards. So that's 13.5. The next step is you have to sum every single one of them together to get. Just keep going. To get a total. That's what this. So this is what this one is. This part of the equation. It's really just take all of those together and add them up. So this added together equals 85.5. And then this added together, Nick, it equals
85.5.
Crazy, right? The next step is to take the sum of the individual's areas, just separately. And that's what this means, right here. This means the areas of each shape added together, okay? So it's just 18 plus 9 plus 4.5 to get 31.5. Simple, right, when you break it down. It looks a little scary, but it's really not.
It's just the big E is all that's scary.
We did that. Finally, all you have to do is take 85.5 and divide it by 31.5 to get 2.71 for the x. Now you have to do it again for the y, but lucky for us, it's the same exact thing, so it's just 2.7. Again, 71 again. And then, finally, all of this accumulates to the final centroid for the figure. So, since it's a little messy, I'll draw you a new one.
parallel circuit.
I'll draw you a new one. Yeah, here. Shapes. Fine.
Move your variables in which you plug in
So,
for your power.
finally, it's 2.71 away from this side.
Variables. It's I equals V over R.
2.71.
Plug in 12 here and divide by your resistance of 20 ohms.
To get your centroid of the figure. And that works for each one. It hits the base on this one, it hits the center of this figure, and hits the center of this figure. And that's how you find a centroid. Now there's another alternative way. Personally, I don't like to use it, but it's the subtractive method. It's the same formula, but instead of you creating separate shapes on the inside, all you have to do is just add this blank area right here. And sometimes it's easier for a shape like this, but a lot of times it's not. So you just do the area, which would be 6 times 6, because you added this shape to get 36, and then you subtract the area of this, so 4.5, because that would be the equal. And you would find the centroid for this one, which would be 1/3, 3, 1/3, 3, so 1 and 1. And you find the center of this, which is, which would be the center of the 6 times 6, so 3 and 3. And then keep going. And then you would do the same equation. You'd add up all of this, the two things, the two missing, for the x, but you'd only have 2 now. And then you'd add up the y, and then you do the same formula. But the problem is now you're working with negatives, because no matter what, this number is always negative in the equation. So I personally like to stay on the positive side, and it goes just a little faster because we have to take away the negative. And pretty much it all accumulates in this step where we add everything together, and you would get the same exact numbers. That go. So the next section that we're going to talk about is the intro to structural member properties. Structural member properties include moment of inertia, stiffness of the object, and in general the overall stuff of the actual material being tested. Moment of inertia is a mathematical property of a cross section measured in inches cubed that gives important information about how the cross-sectional area is distributed over a central axis. So moment of inertia is two ways, either as a joist or a plank. So either it's laying down or going up. So So moment of inertia can be calculated as I xx equals base height over 12. Base equals base inches, and then height equals height inches. So when I think like this, go. 1.5. After you do all of the equation, it's really just a put in and plug. It's 1.5, 5.5 cubed divided by 12. After everything gets put in together, you get 249.5625 over 12. You divide, you get 21 inches to the fourth. So now if we flipped it, it's going to be a lot less. So it'll be actually 1. So if we did it as this view, mathematically, you're not going to have the same amount of numbers, and it's going to be a lot less, and you're going to get 1.5 inches. Alright, so next is modules of elasticity principles. You're going to need this to solve modules of elasticity. And the equation,
This is for calculating beam deflection.
is the max beam deflection was FL cubed over 48. So you can use this for like a whole lots of things. and it's force
Pretty much used to tell how bendy something is.
times length. Yeah, pretty much over elasticity and then length again. So we can use the Douglas fir that we just had, right? We've got the force weighing down on it. Let's just say it's 250, right? And then the overall area, which is 96 inches, that is given to you in most problems unless you're working backwards. Times 48 times elasticity, which is ridiculous number that you usually have to find. It's usually in the millions. In this case, it's 1,800,000, and then 20.80, which is what we got.
Cube the 96.
What?
Cube the 96.
96 inches is given to you. That's the length.
Cube it.
And then altogether you get 0.12. And that's the same for anything. That's the same formula every time. And that's it.
Start. Okay, free body diagrams are used to pretty much show simple forms of forces and force objects. Like here's an example of a pulley system, and you use arrows that go different directions.
And that shows the direction of the force.
Or use angles. Okay, here's an example of a truss. And you can show the force that are pushing down and up, and this is pretty much what you use to show people what's going on. You can also use rotary forces. A straight line, push or pull acting upon an object, vector quantity, has direction and magnitude, is pretty much a force. And you can have it going different directions, just to show which way something is turning, clockwise or counterclockwise.
He's talking about moments, the twisting effort about a point or axis when the force is applied at a distance. Either counterclockwise or clockwise.
And moment equals force times distance.
Distance from the
point of rotation. And we'll say like sketch some books. So we have like here's a book, and we'll say it's sitting on a table, and gravity's pushing down on it, which means the table's pushing back up on it to keep it
and that would be an example of a very basic property. So next what we're going to talk about is we're going to talk about joints in an area. So there's two types of joints. There's a roller joint, which is a circle, and a pin, which has two forces acting on it, and a roller only has one. Rollers go horizontal, vertically, and then pins are simply are horizontal and vertical. These are extremely important for truss solving, so you need to know. Every point either has a tension or not tension,
Compression.
or compression, and as they're being pulled and pushed throughout the areas, the different forces are acted upon them, and that's why you need a body diagram so that we know where the forces are being pushed and pulled.
Alright, cut. Now we're going to talk about force vectors. A vector has both magnitude and direction. So for this we're going to use just our normal graph. And this is our x and y axis, right? So the length, and for vectors are represented by arrows. So say we're just going to draw that's a vector. Okay? They include magnitude, direction, and sense. Sense is like direction. Like it could be going that way, or that way, or that way.
Up to the left, down to the right, stuff like that.
Okay.
Magnitude is the length of the line segments within the vector. Direction is the angle between a reference axle and the arrow's length angle. That 30 degrees is right there. And sense is indicated by the direction of the tip of the arrow. Alright, in trigonometry.
We use pretty much trigonometry to find out this. So see this vector right here? If we just draw a dashed line down right there, and then a dashed line right there, we have a triangle, which means if that's 90 degrees, at 60 degrees, we can use
Sine,
trigonometry to
cosine, and
figure out
tangent.
the length of the hypotenuse and the length of this and this, if we have one of these sides.
So pretty much magnitude can be used as the same exact thing. That's a force, all right? It's the same thing as a force, but it also can be seen as distance. So you can find using trigonometry if this were to be equal to 75, if this was the magnitude, and this would equal 35 degrees. you can find trigonometry, even though this is a force, to find the forces on the opposing areas, the opposing Fy and the opposing Fx. So pretty much, you're going to use cosine, sakato, right? Sine, adjacent, cosine, opposite, and then cosine, adjacent, sine, opposite, and tangent. Yeah, I was right.
I know you said it wrong the first time. No,
Yeah, I
you
was right the
weren't.
first time. Cosine is adjacent over hypotenuse.
Yeah, you
So we're going to talk about cosine.
You was wrong the
To
first time.
find F. Sorry. Sorry. So this is at the opposite F of A, X. All right, because this is the distance away from the object, and then the S is a Fy, AY, just for the momentum. And the A's and the X's aren't just they're just messed up. So cosine equals adjacent over hypotenuse. And when you throw everything in, 35 cosine 35, and then adjacent x over 75. Once you solve it all out, all you have to do is multiply each other together. You see 61.4. 61.4 as your the next is you use sine, which is the same thing. Same thing, except you're using sine. And this is opposite over hypotenuse. Right? So then this would be opposite. And then it's the same principle, except sine. You multiply and you get 43.
Corinne.
So resultant forces are forces made. This all cumulates together to resultant forces. These are forces that are made when two vectors, such as this and this, pull away from each other or in the same way. So let's just say this one is just a little deeper than that one. Alright? So let's say this is 60 and this is 30. Alright? Hit.
Find velocity, you get the distance.
So you're giving the tension, right? You're giving, sorry, not that. You're giving the power for each, and you can just you need to find this. You need to find how much it's being pulled in one direction. Alright? So, you guys know the formula now, right? It's just cosine 60. When you hand it, slam it all together with the 300 times sine 60, you get 260. Next part is you've got to do this part, top one. And since we've already found this one, this will be negative. Alright? So we do this is 400. Same thing, literally the same exact thing. To get negative 200 pounds because it's being pulled in the opposite direction. Hit it. So then you take them and you add them together to get the upwards. Alright? So it's 260, 200. We cut out some stuff, but it ends up with 59.8 because these are just ranges. So this is the this is how much it's moving down. So, and then we do the same thing, except opposite with sine, to find this force on each of the vectors, right? And then you just add them, it's literally adding them together, super easy, and you get 400.
A sprocket is when
96.4. Now remember, one of them will be negative if it's going to go in the opposite direction. So now we know that this accumulates into this. Right? So this is 494, 96.4, and then this is 59.8. And we got these numbers from here because we learned them from here. And then, really, we all know a squared plus b squared equals c squared, which is the hypotenuse theorem, right?
Right.
So, right, thank you, Dave. So you just square these, which is all together a lot, a huge number, and then C, because you just put over just to find it to reduce to C, and you end up with
Pythagorean theorem.
500. So this is
500.
500 fourths, and then you just round it, and then since and then you can then use Sakator again to find this at 7 degrees, and then you just found your force. Good. Congrats.
Hooray!
And